Okay, can you guys see the screen share?
Yeah.
And then it's going to get kind of messy when I annotate it, but we'll see how this works. Okay, so question one was really about rotations and sort of a question about reflections, if there is one. So the first question is, does this represent a transformation from an orthonormal basis like XYZ to another orthonormal basis? I think just based on my glance over the quizzes, this is what got a lot of people, is that you guys knew that the columns of this represented the new basis vectors. It's just, or columns or rows, it's just the question of, well, is it the columns or is it the rows? And if you wanted to prove it this way, so there are two ways of showing this. One way is to pull out the individual rows of the new basis and show that they satisfy the properties of an orthonormal basis. So this is a rotation. And then let me just multiply it by the unit vector in the x direction. So the unit vector in the x direction looks like this, 1, 0, 0. And so what I get is that 1/2 from out front, and then aha, it's going to come down and select this. So, you know, the kind of meta structure of this linear algebra thing we're doing is that vector times matrix equals vector. So when I multiply this vector, namely the x unit vector, by r, what I get is this, √2/2, 0, minus √2/2. So that's a vector. And in fact, what that is the unit vector x expressed in the original coordinate system. Or sorry, expressed in the new coordinate system. So that's one way of figuring out, oh, should I use the rows of this or should I use the columns of this? Just realize that, well, I could multiply it to make sure, but row vector multiplied by r should be row vector. So one way of proceeding is to pull out the individual new unit vectors. So, or we haven't shown their unit vectors yet, pull out the individual vectors, which are the row vectors comprised of the row of each matrix, each row of the matrix. So 1/2. And then what do I have to do to these things? We'll call them E1 hat, E2 hat, E3 hat. So these should satisfy two properties. What should be true about this, expressing both of those properties in like one foul swoop?
They should equal 0 if they're orthogonal.
Yeah, if k doesn't equal j, I should get 0. So if I dot product E1 with E2, what I get is √2/4, 0, minus √2/4, so that's 0. What if j equals k? So I take, for instance, E2 dotted with E2 itself.
You should get 1.
Yep, so that's the normal part of the orthonormal. So we sweep this all up in the symbol, the Kronecker delta symbol. So that's doing it by parsing out the individual rows. There's another more succinct way of saying that, is we can just take this, r jk times r ki, sum over k, which is the laborious way of writing matrix multiplication. And then this should be equal to, so we got rid of the k index, we summed over it, multiplied by it, delta k, or delta ji. And it turns out this is actually, every time I dot product one of these vectors with itself, I get 1. And every time I take the dot product of one of these vectors with a different one, I get 0. So it is an orthonormal basis. So any questions about that. Okay, the next one is easy math, maybe not so easy concept. And there are two ways of doing this. And they give you hopefully the same answer. So find the angle in between the pre-rotation x, I guess I need the matrix, pre-rotation x-axis and the first unit vector of this basis. So one thing you could do is realize that we actually have pre-existing technology before this class to do stuff like that. Don't worry about the fact that they're wearing hats instead of vector arrows. This is a dot product, and it's got the geometric meaning of I e1 cosine of the angle in between them. The other thing you could realize is that the named direction cosines for these for this matrix is meaningful. And if I want to know how to get from old basis 1 into new basis 1, I just pick the 1, 1 element of this matrix. If I wanted to know how to get from old basis 2 to new basis 3, I pick the 2, 3 element of this basis. And that's the dot product that I care about. So you could either do it the long way and actually literally dot product these out, which would look like dot product 1, 0, 0, and then dot product, again, we know it's the first column now, so root 2 over 2, 0, minus root 2 over 2. Okay, this is going to be this element. Remember the 1/2. That's what the direction cosines mean if you just kind of interpret them directly. Or we know what the x-axis looks like, and then we know what the E1 vector is, so we could just dot product them manually, but you would get the same answer, I hope. Okay, root 2 over 2 is the dot product. What angle corresponds to a cosine of root 2 over 2 without having to do too much work? And we'll call this theta 1, 1, because it rotates our old first basis vector into our new first basis vector. Radians or degrees are both fine for this.
45 degrees?
Yeah. So 45-degree angle. Again, the two ways of doing it is without, it saves you all of 20 seconds of work. But for instance, this, remember the 1/2 out front, this is the 3, 1 direction cosine. And then, for instance, these are what these things mean, is this would be the 1, 2 direction cosine. Or you can just dot product them. Okay. Any questions about that? Okay, I'll try not to do this too much, but there really isn't too much I can do in a class that only meets twice with the kind of funky quarter we have. This is a homework problem. The easiest way of solving this would be a homework problem. You could write down two things, like I could write down A and B with similar elements. So two arbitrary vectors, and then I could transform them and write down their pre and post reflection coordinates, and then maybe try to compare them, see what's going on. That would, you get a lot of at least like social credit for that, because that's, you just like jump right into it, good for you. What's the elegant way of determining whether or not we went from a left-handed or right-handed coordinate system to another left-handed or right-handed coordinate system as per the homework?
You can check to see whether the determinant of the rotation matrix is positive or negative.
Exactly. So we can just take the determinant of this matrix, and if you do, it turns out to be positive. So that means we don't change handedness. Okay. And that's really what's going on. Is there's a convention that says that when I create C from the cross product of A and B, I use my right hand to break this degeneracy. That is a convention. If you met physicists from like Alpha Centauri who are primarily left-handed, they might have a different convention. It's not physics. We just had to choose one. If you reflect from a left-handed coordinate system to a right-handed coordinate system, all of a sudden your unit vector or your cross products are going to be flipped. So if it's not invariant under rotations, it's probably not physics. So I will not say the same thing about reflections because there's some really interesting stuff that goes on in particle theory about that. And it kind of blew people's minds in the mid 50s when they started discovering that the universe actually does have a handedness, actually.
Isn't that like electron spins always go one way for like certain like decays or something?
Yeah, exactly. So if I have, I don't know, like a radioactive cobalt nucleus or something like that, and it emits a beta particle, which is a needlessly pretentious way of saying electron, is that the nuclear spin being oriented in some direction will mean that this is preferentially kicked out to the front versus the back. And if you have, you know, the radioactive cobalt nucleus and an electron pointed down, you'll likely get it to kick out in the opposite direction. So nature does have like kind of a preference for left-handed or right-handed, which is kind of bizarre. And then people try to connect this to stuff that you see otherwise. So like snails, they all have, you know, their shells are like screw shaped. So that screwing has a handedness too. I think snail shells are right-handed. So as you follow the curvature of the shell in, you've got to use your right hand if you want your thumb to point in the direction the snail shell points. And people are like, oh yeah, you can trace that right-handedness back to like, you know, the fact that particle physics also has a handedness, which I don't know if that's true, but yeah. You got one more year before you guys get to that stuff. Okay, but any questions about question 1? Okay. Question 2, really just kind of crunch through some stuff. We'll test my ability to do this really quickly without making any calculation mistakes. If you catch me making a calculation mistake, I will give you extra credit on the quiz. So we want to calculate the divergence of this vector field. So it is in Cartesian coordinates. We don't know how to do non-Cartesian coordinates yet. So I will write this in this notation. So this is signed for d by dx and d by dy and d by dz. So just suppressing that extra d. So you'll see this a lot as you get into upper level math and physics courses. And then we want to dot that with f's x component, y component, and z component. And so I get d by dx of this stuff. I don't see anything in there that depends on x, so that's gone. And then I get d by dy of this stuff. I do see stuff that depends on y, so I'm going to get 2 beta xy. Let me double check that. Because we put stakes on this, yeah. And then here we have gamma y squared over z, so d fz by z. There is something that depends on z. We'll get a minus sign, so minus gamma y squared over z squared. Is that right? That's right. Okay, so I get a scalar function at the end of the day, which is what I want. Divergence should produce a scalar function. So divergence of f is a scalar function. That's just 2 beta xy minus gamma y squared over c squared. Gross. But this is just testing your mechanics, really. Any questions about that? Okay, here's the one that I am likely to mess up because there's a lot of signs to keep track of. In Cartesian coordinates, our curl is the determinant of this sort of stuff, d by dx, d by dy, d by dz. Notice I keep saying in Cartesian coordinates because really quickly we're gonna, maybe actually by today, realize what a mess these things become in curvilinear coordinates. And I won't give away why that is yet. Okay, so our I hat is partial y of the z component. Oh crap, there is one of those. Yeah, let me just give myself a lot of room for this. Partial y of the z component, so that's 2x y beta. I thought I was going to forget the beta. 2xy beta, that's partial y with wait, no, it's not. Partial y with respect to z. That's 2 gamma y over z. And then minus partial z with respect to y, that's the part I just did. So 2 beta x y. All of that is the I hat part. So that minus that. And then big overall minus for the y part. So the j hat component, that's partial, the z component, partial derivative with respect to x, nothing there. Something's working out for me at least. And then minus partial x component with respect to z, there's no z in there, nothing there too. So that's nice. And then finally we get the plus, because it's an even permutation, the k hat part. So second component partial with respect to x, such a thing exists, there's an x in there. So I get beta y squared. And then partial x component with respect to z, there's nothing there. So at the end of the day, we get something that looks like this. Just kind of grubby x component, and then everything else is okay. So factor out the 2y. And then 0, and then beta y squared. And that is a vector, which is what we want. Okay, any questions about any of that? Okay. Just before we get started on new stuff, where are you guys at in classical mechanics?
We've been doing like moments of angular momentum. I think we just started on energy and like energy as like the negative gradient of potential in the last class.
Okay. So yeah, we're basically going to do, yeah, so we're going to get to something that maybe you guys will be asked about in next class. So yeah, I was kind of hoping we'd be synced up a little bit better. So this is either going to be perfect or a little bit off. Okay, we have one topic to get to before potential theory. You guys haven't covered whether or not force fields are conservative or not, though, right?
I don't remember.
Okay. Which probably sounds like a no. Because usually when people get there, they're like, this is the coolest thing ever. You can like learn so much without doing any work.
Yeah, we've talked about it, but not without doing any work. We have to do work still.
Okay. So yeah, we'll be no taking curls to show things are conservative instead of line integrals. Great. So we'll get there today and you can say like, oh, we know this stuff. Okay. So we're kind of in fundamental theorems of stuff for vector calc. And this is how it works for single variables is that integrals undo derivatives is kind of how you were probably first exposed to this, and you're like, okay, that's great. And you knew that because Calc 1 and Calc 2 are called Calc 1 and Calc 2. But there's something really interesting about this, is that if I have a function, you know, that's differentiable, so it satisfies the fundamental theorem of calculus, there's all this stuff in the middle that I don't know about. So I can, again, go in a straight line in between A and B, or I can go in this like kind of wacky roller coaster kind of trip in between A and B. And a lot of in that second, what is that, fuchsia? I don't know. That second kind of purple pinky curve, a lot of stuff cancels out. There's a lot of up that gets canceled by some down. And in the calculus of vector fields, there are a couple of important versions of that. Gauss's theorem, also known as the divergence theorem, which says that if I have a whole bunch of sources and sinks inside of a volume, all I really care about is the net sources and sinks. And the only way that that shows up is by the flux through the surface. So I can look at the flux of the vector field through the surface. I'll call it V dot D sigma. And this is a closed surface. So in the context of electromagnetism is really, you know, probably how you'll see this most frequently, is I might have a negative charge, I might have a positive charge, so this would be a source of electric field lines, and the negative charge would be a sink of electric field lines. And then I have a whole bunch of other stuff that maybe I don't even know. All I really have to do is pay attention to what's going on at the boundary to learn something about what's going on inside, but just like the single variable version suggests, not everything that's going on inside. Okay. So those two are kind of a thinky warm-up for the hardest to visualize one, which is Stokes' theorem. It should be AKA, of course, the curl theorem, but I'm not going to do that because people don't do that. I don't know why, to be honest. Let's say that I have, you know, again, think about a wire that's been dipped in soap and you're using it to make a soap bubble. So the lavender is the soap bubble that's coming off of this. And then the wire is the edge of the surface. So I have a surface S and it's got a boundary in this blue line. So Stokes' theorem says that all of the curl in the surface can be related to the action or behavior at the boundary. So I want to take all of the curl in the surface and I have to dot it with this element. So I take the curl of the vector function, then dot ds, and then I do a surface integral. So this will be your favorite thing ever in vector calculus, I promise. And I can relate it to just a plain old ordinary line integral at the edge. So this is a closed line integral at the boundary of S. Okay, so what if I did the thing that my hand, just by kind of training and habit, wanted to do and made this like a closed surface? What's true about the curl of a closed surface if you integrate up all the curl? So for this second, the right-hand side, I'm integrating up all of the a dot dl, whatever that is. around the edge of this boundary. So basically, the wire that makes the soap bubble or the edge of the grocery bag or something like that, if this becomes a closed surface, what happens to the opening? It's probably the most like leading way of asking it. So as the opening closes, I have basically absolutely no distance to integrate over, right? So that becomes zero. In fact, this is the basis of a theorem in black hole physics that gets kind of cheekily described as black holes have no hair, is that there's no curl on the surface, the event horizon of a black hole. So I'm not going to prove this because we kind of, or at least on the auxiliary videos, there's a proof of the divergence theorem. It follows the same pattern. So I'll just say how you would do this if you wanted to do this. First, you would show that at an infinitesimal level, you can express the curl of a vector field in two different ways. So this is a primary definition. As a limiting form. So Cartesian coordinates are fine because you're going to be taking this delta v goes to zero. You can show that at an infinitesimal level, essentially Stokes' theorem holds. So you can replace this by Taylor's theorem pushing things around with this. And it's a bit harder than the one we went through. But this is essentially Taylor's theorem, or sorry, this is Stokes' theorem at an infinitesimal level. And then what you do is you calculus up the big surface. And I'll draw a picture of that because that's kind of the heart of what's going on is, okay, imagine that I have two little plaquettes of area side by side, and I blow them up and look way, way, way close in. Right, so here are two side by side little bits of delta S, delta SK and delta SK plus 1 or something like that. And then I start looking at the curl or the line integral around the edge of this boundary. So when I'm looking at the curl, I'm looking at the circulation of this function. So I might have some line integral here. And then because we want to be pointed out of the surface, at least the way that I kind of hope to draw it, I actually want to flip those. So I screwed that up. I want to point out of the surface. I got to use my right hand. I want to circulate in the counterclockwise direction. And this is important. Okay, what happens if I want to talk about this neighboring? So this is like a little tiny bit of this line integral, integral a dot dl for some delta sk. And then the one next to it is this little line integral, closed loop line integral, sk plus 1, its neighbor, a dot dl. So I'll do this. Got to keep going in the same direction. What happens when I get to this side that they share? I get literally the exact same piece. I get a dot dl, but one of them, my dl is going down, and the other one, my dl is pointing up. They're off by 180 degrees. The dot product for one is the opposite of the dot product of the other. They cancel. So all of these things, the reason I call them all fundamental theorems of integral calculus is because they all have this property where a lot of the stuff in the interior cancels out, and you're just left with stuff at the boundaries. So for all these internal plaquettes, I get a little loopy line integral with a down piece, and then its neighbor has an up piece because we're keeping the same direction of circulation. Those all cancel until I get to this boundary. So again, stuff at the interior of the surface all cancels out. All I care about is what shows up at the boundary, provided the curl exists and the thing's differentiable. Okay, any questions about that? Much more important is, how do you actually use the thing? Okay. We could do this like no luck. Before I write down the example, do you guys want to try it yourselves or go through it together? Or give you guys like 3 minutes to just see, like check in?
Sure, sounds good.
Okay, so put a 3-minute timer on this and see how far you get. I think it would take me longer than that. So just see how much of a good start you can make. Okay, so we're gonna ask you guys to verify Stokes' theorem. On the following surface. So I got to tell you two things. I've got to tell you a surface and a function. So the surface is going to be this. It's just going to be the plane that goes in this little quarter circle on the YZ axis. So just this flat quarter circle plane. And then I got to tell you a function. And the vector function is going to be, so I got to give you something that looks weird because otherwise the curl will vanish. So it's got to have some non-vanishing curl to make this even remotely interesting. And then timer starts now. Okay, that was a really quick 3 minutes. Well, so any questions with anything people ran into while they were working? Okay, so we'll say that especially the line integral part, there is no one unique way of doing it. So there is a little bit of freedom that you guys have. But yeah, we'll get to the line integral later. The more interesting part is this part. So what we want to do is we want to verify that integral f dot dl along the boundary of this surface is equal to, oops, f, the curl inside of the surface. And this thing on the right-hand side is just like a beast. So let's do that first. Okay, what coordinates do you guys want to use? It's sort of a trick question. Do you guys know how to express the curl of something in non-Cartesian coordinates? No, so yeah, we're kind of stuck. So let's do the easy thing we can do first. I mean, maybe you get lucky and this whole thing just turns out to be 0, you know? So The other thing is always do differential calculus first because it's easier and you feel like you're making progress instead of just staring at a blank page and wondering why you chose this major. At least those are my memories. Okay, so take the curl. What I get is I got nothing minus 1, so I get minus 1 I hat. And then for the j hat, there's overall minus 1 minus 0, so that's minus 1 j hat. And then for the k hat, I get minus 1 k hat. So that's nice at least. Get that for the curl. Okay, so here is the first subtlety and choice, is that this is not a closed surface. So when we're constructing the d sigma, so we've got that. Now we got to work on the d sigma part. Which way does d sigma point? For a closed surface, it would point outside of the surface. For an open surface, we have this ambiguity. And I told you one way of resolving the ambiguity is to define the thing, keep the ordering of the cross products. So what is a little piece of the surface? So at least like the magnitude part of it. I make a tiny little piece of d sigma. What are the two actual coordinates that contribute to that? D what and d what?
dy and dz.
Yeah. So essentially, this is how you just keep the same ordering. We go x, y, z. And the fact that we do x, y, z is because we keep things right-handed. If you had a y, x, z coordinate system, it would be right-handed and things would seem weird. So the usual convention is to keep your ordering. Okay, so what this is dy times dz and then j hat cross k hat. What is j hat cross k hat? Start with the fingers of my right hand in the direction of j hat, curl them towards k hat. I end up pointing in the x direction. So this is dy, dz, I hat. So that's good progress. We got that. And then it's just integrating this up over the quarter circle, and that's going to be actually really nice too. So I have integral s. I'll just write it all out because this looks cool to write out. Integral s, we'll deal with that later. That's going to be some type of double integral. Minus 1, minus 1, minus 1 dot dy dz. That's the I hat piece and nothing else. Great. What is that?
Negative dy dz.
Yeah. Okay, it's easy to get lost in the weeds here, but this is really the following. Or negative d surface d area. Okay. What is this?
It's whatever the area value is, just negative.
Yeah, and this is a quarter of the unit circle, right? So the unit circle itself is pi, so this is pi over 4, so that's minus pi over 4. Okay, we'll say kind of like part of it is sociologically where, you know, people want you to learn the mechanics of how to do this stuff without destroying you with really hard problems. But part of it is like in actual papers where you do actual integrals and you do actual physics. A lot of the times this will turn out to be the case where just like the integral, once you set it up, it's like pretty close to trivial, or it's so hard you feed it into a computer. So this isn't like a stunt integral. This is something that you might actually potentially look at if you were doing some like fluid flow. Okay. So that was the right-hand side. Any questions about that? Okay, the left-hand side is going to be closed integral f dot dl. This has two easy pieces, easy-ish pieces, and then this kind of curvy part. So we have to do the entire line integral. I'm going to put a direction on it. The direction also needs to be right-hand rule compatible. So this needs to point in such a way that we get the same direction. So we circulated in such a way to get this I hat as our area vector. So if you put the thumb of your right hand in that direction, your line integral has to circulate in the same way. Otherwise, you'll get a bad minus sign. So we also circulate. We had a choice. Nobody told us. Sometimes when you're given a line integral, you're told which way you got to circulate. But in this case, we weren't. So we had to resolve that ambiguity such that both of these things are the same. So I'm going to circulate in the right-hand rule direction so that I get my thumb pointing out in the I hat direction. So this would be path 1, this would be branch 2, and this would be branch 3. So branch 1 is just down the y-axis, branch 2 is the quarter unit circle in the YZ plane, and then branch 3 is down the z-axis. Gross. Okay, but 2 of these are going to be nice. One of these is going to be, I think, the first example of an interesting parameterization that we've done so far in this class, at least. Okay, so I'll write that, and then we'll just do them piece by piece. So what is, for Roman numeral 1 going down the y-axis, what does that part of the integral look like? And then up here we have our result so far, that this equals minus pi over 4. Okay, what is DL for Roman numeral 1?
It would just be dy.
Yep. And because it's got a arrow hat, it's going to be dy pointing in the no trick question j hat direction. So just writing everything out like vectors, this line element is that. Okay. So when I express this, I get z dy. Okay, the limits of y go from 0 to 1. What is the z value along this? And what is this piece of the integral turn into?
Z is 0, so it's just 0.
So 0. Isn't vector calculus easy? Okay. Let's do 3 before doing 2. How about that? Okay, so for 3, we're going to get something similar. I'll give you guys a minute, see if you guys can get it without any prompting. And then we'll do 2 together because that has interesting parameterization, like how would I express this along the unit circle? Okay, for path 3, what is my DL?
Is it dx 0, 0?
I like the 2 zeros, so I'm not moving, I'm moving in a line, and the line is going down an axis, one particular axis. So 2 of them are going to be 0, but which axis am I moving down and in which direction?
It negative dz.
Exactly, right? So I'm moving down, so the negative dz. So I'm not moving along the x-axis, I'm not moving along the y-axis, and then you even got the negative part right, so it's minus dz. Right, the x that I think you're thinking about comes from the fact that there's the x component, which is the thing that I get after I dot. So that's third branch, that's x minus dz. What is the value of x along this path? And then what is my integral?
It's going to be 0 again.
Right. So this path is parameterized by, I'm on the z-axis, so that's 0, 0, z, and z changes from 1 to 0. So that's 0. So far, so good. I really hope this last part equals negative pi over 4, or else we broke a theorem of calculus. So the last part is this. Okay, before I write it down, can anybody think about a way of expressing this quarter circle, which was probably covered on like the first or second day of your trig class?
I parametricized it where you like set up the z and y components as like trig functions.
Yep.
For t.
Yeah, the only thing you have to do is figure out which one's sine, which one's cosine, and which one's 0. So x is always 0 along this curve. Y starts at 1 and ends at 0 along this curve. So y of t, we could, what starts at 1 ends at 0 along that parameterization. So that's cosine of t. And then z of t starts at 0, ends at 1. What are we doing? Sine of t. Sine of t. So that's a good parameterization. And what we're going to end up doing is, so just kind of holistically, this is a line integral. I should only have one integral, right? So that integral is going to be t as t goes from 0 to pi over 4. But I end up with a parameterization, and the parameterization is going to show up in two places, in the differentials and the things themselves. Okay, so for 2, curve 2, x is still always 0, but we'll write it all out anyway. So this is y zx dot dy dz. So we could move in both of those directions. And then this is 0 because we're in the yz plane, and this is 0 because we're not leaving the yz plane, right? So that's just, you know, flat quarter circle. And then we'll do one more thing, and this is as bad as it's going to be. You know, if we hadn't talked about the parameterization first, this would just look like really crazy, to be honest. So we have y dot 0, we got z dot dy, and then we got 0 dot dz. So actually not that crazy. We have z dy. And what we know is we're going to parameterize this with t. Z is sine of t. And then what's dy? Well, dy is d cosine of t, because that's what y is. And then we're going to go from 0 to pi over 4. Excuse me, pi over 2. So to pi over 2, we got sine of t, and then d cosine of t is minus sine of t dt. Minus sine squared t dt. And like, I'm okay with you guys saying this is the point at which I go to Wolfram alpha. There is an amazing trick for sine squared and cosine squared integrals. And the trick kind of goes like this. I'll just put it up really quickly and then erase it. So they both repeat in between 0 and 2 pi. But then if you square them and you make the negative positive, they both repeat in between 0 and pi, so that's helpful. And sine, for instance, sine squared looks like this. And cosine squared looks basically the exact same, but shifted. And by symmetry, what's true is the integral of sine squared and cosine squared from 0 to pi, or pi to pi over 2, or 0 to 2 pi, or actually, if you even look at the lumps themselves, pi over 2 to pi, or 0 to 2 pi, they're all the same. But then there's something else you know. So first you know that the integral of cosine squared over a lot of important integrals is equal to the integral of sine squared over a lot of important integrals. But then what do you know about this? Cosine squared plus sine squared, for like anything, literally.
It's 1.
1. So integral 1 dt I can do. And because these are equal, you can figure these integrals out for the most part. So that's a helpful trick. But to be honest, at this point, I would let you guys Wolfram alpha it. One way or another, what you're going to get is that the other way is to use a trig identity. So you could also say that this is equal to 0 pi over 2. It's got like minus 1 minus cosine 2 theta over 2 or something like that. Sorry, we're doing t. So you could use a double angle formula if you wanted a third way. This only works over this particular interval. But anyway, you get minus pi over 4, one way or another. So life works out. Okay, any questions about that? up to the part where you do the integral. And at that point, like something of this complexity, I'd say you can look it up. Okay, here's the really important punchline. I'm going to ask you guys to do one more integral. And I'm just going to clear everything and redraw it because that's faster. Okay, we're going to do x, y, z, and then we're going to have this area where we go in between the origin and 0, 0, 1 and 0, 1, 0. And I want you to calculate this. For A equals, just make sure I did this the same way. But I'm just going to change the surface. And the surface is going to be this cylinder that comes out and then comes in like that, and then it wraps around there. And then I'm going to put like a weird bump on it right there. And then just to be like super crazy, I'm going to put like a hole, like a donut hole right in the middle of my surface. And I want you to find the surface integral of the curl on this crazy looking thing. What is that? I can do that integral in my head, even though you haven't even told me a mathematical function that describes the crazy bump, soap bubble, hole, pickle surface. This is the important part about Stokes' theorem. This is equal to minus pi over 4. It's equal to the exact same integral as the easy surface that we laboriously computed. The point is that all of these surfaces and anything in between, so again, imagine a wire that's been dipped in soap solution and you start blowing bubbles, right? All of the bubbles, like all the infinitude of bubbles that you could possibly draw, all have the same surface integral of their curl because of this cancellation effect. So this is what we mean by the crazy behavior in between in the interior doesn't show up at the endpoints because all of this up stuff here cancels with some down stuff there. Right? So all the goofy stuff in the interior only manifests itself at the boundary. So this is how you guys can essentially use these to do really hard integrals really quickly. Somebody might present something that's very difficult and you're like, I could probably come up with an easier surface, and you're free to do so. Okay. So any questions about that? Just take like a minute and let everything sink in because we're about to change topics. It's kind of a logistical note. If we finish, so this is math methods, so our discussion of potential theory will not include any potentials, really, like physics potentials. We'll just talk about their mathematical properties. So really we got like 2 more pages before we get to curvilinear coordinates. But hopefully those 2 pages are something that you don't have to redo in classical. Okay. So we'll start with Newton's second law, and it turns out that, you know, hopefully your mechanics instructor made a point of this to some degree. is that Newton's second law really is the work energy theorem and is the impulse momentum theorem. If I just look at Newton's second law, F equals ma, and I kind of look at its mathematical properties a little bit. So this is F, and this is the second derivative of position, and we'll just keep it to X. And for now, at least, get rid of that hat. So we're just in 1D. And F can point in the positive or negative X direction. So calling it a vector is a bit superfluous, even though it is a vector. Okay. So first you did this sort of stuff and you talked about simple arithmetic problems in 1D to learn the units and stuff like that. And then you did this in 2 and 3D where you had to learn about the vector addition. And then all of a sudden at the end of the class, kind of the wheels came off the bus a little bit, and all of a sudden you're given a problem like this. So imagine the force of friction from a bumpy surface. And all of a sudden we're in this kind of wild mathematical scenario where F, by virtue of being F of X, it's a function of X. Well, what you're used to doing is finding X and then using that to determine the kinematics or dynamics of the particle. So find F, use F to find X. But now you don't know X. So you need X to find F, and you need F to find X. The force tells the particle how to move, but the position of the particle determines the force. So this is a bad situation to be in mathematically, right? Need to know the position to find the force, need to know the force to find the position. This is why the work energy theorem exists. And what somebody pretty early on asked is, well, what if I just look at like the aggregate effect over some contour? So we'll go right to vector calculus. And I'll look at, and these are all FNATs, and just, this is about the limit of my drawing little letters. F dot DL or DR. And let me just look at like a tiny little piece, right? So F dot DR. And I'll integrate both sides of this equation and see what happens. MA dot DR. And then what I can realize is that over some little contour, and let's pretend we're not doing rocketry problems, so the mass is fixed. This is dv dt. Okay, this is one simple trick that physicists can do, but mathematicians will hate you. What's the trick that I do to get this goofy looking stuff with all the d's into one single expression that has one variable of integration? So if you think about this as a little piece of r, and you think about this as a little piece of time, and you think about that as a little piece of velocity, and so they're just numbers, right? Or in this case, they're vectors. I can just associate them however I want. Like we haven't done anything that's, we have one example of something that doesn't commute. We have no examples of things that aren't associative, which means you're free to multiply things and divide things, any way you want that satisfies order of operations. So I'm gonna group the dr with the dt and leave the dv, who used to have the dt, below it all by itself. But what is dr by dt? So now I have something that has a single variable. And then I have something that looks like this. And voila, I have the work energy theorem. So we declare this to be something called work. Literally just made it up. So the work of a force field is the integral of F dot dr along the path that you take. right? So that's the work along that particular contour, and that's related to a simple scalar quantity called the change in kinetic energy. So that's the work energy theorem. It literally is Newton's second law. And the first time you saw this, maybe this was like kind of glossed over, but we're not going to do that. And we're going to point out something that is now suddenly important to us because we might have interesting forces, like we might be doing fluid dynamics. So here is the XY plane. And let me, because I can draw this, talk about a 2D force. So maybe think about like you put like a little paper boat down on a pond or something like that, and then it floats around on the surface. And the game is every point in the surface, you tell me, I have to draw where the force is. And then maybe we have like a whirlpool. So maybe the force looks like this. And then I ask you what the work done by this force is as I go from point A to point B. And so really clearly, if I go from point A to point B along different contours, I'm not ruining any suspense at this point because we did do an example of a non-conservative force field. If I go from point A to point B along this contour, I've got the current at my back and the force is helping me get from point A to point B. So I expect that force to be doing positive work. However, if I go from point A to point B along this contour, I'm going to get negative work. Contour 2. So generically, it's not true that any force field that you guys can dream up is going to have a contour integral that's independent of path, right? It's just those are the ones that you guys were seeing way back in Physics 1 because you weren't prepared to deal with non-conservative forces. Okay. So any questions about any of that? Long form warning, reminder why we're doing this in the first place, and then warning that we're now in like non-conservative force land. So, and we're going to use abstracted terminology. So we'll just say if a vector field so we'll say if all contour integrals of vector field are path independent. Of course, the conservative comes from the fact that it's conserving your energy, right? So every single joule that you put in, you can get back out later. Whereas friction is non-conservative in the sense that you put energy into friction, you cannot get it back later. Okay. Is it worth reminding you guys of the examples of the ones that you guys have seen and why they're conservative or non-conservative? Okay, so we'll just do it quickly, call and response. Gravitational forces, conservative or non-conservative?
I think that one's conservative.
Yeah. What about spring potentials?
Also conservative.
What about electric fields?
Also conservative.
Yep. What about magnetic fields?
Also conservative?
Yep.
Okay.
What about friction?
No.
Right. So, yeah, so you guys have the roster of forces. There's one extra thing that we can do, and this is going to be presented to you guys as a theorem of vector calculus. So so I'll call it a theorem. If a vector field is conservative, it can be expressed as the gradient of a scalar function. And in math speak, with notation that's useful and leading, so there exists some function u, we'll call it of x, y, and z, such that grad u equals f, which is a vector function with this goofy minus sign in front of it. So the minus sign is a physics convention. It has nothing to do with math. That has to do with the fact that we're talking about the work done by the force or on the by the object or on the object. Okay, and when you're talking about force fields, you're talking about the thing that's putting the force on. And then when you're talking about potentials, you're usually talking about the energy of the thing itself. So that's what the minus sign comes from. Okay, we're going to prove this. And it's maybe going to sound tough, but actually we've already proved it in a sense. And this is how we've so this is like really good stagecraft, I guess, but this is like really bad math. I'm going to tell you what we prove after we prove it, because you guys already like kind of know the answer. You've seen conservative fields before. There is a criterion that tells me I have some f, right? And I want to know if it's conservative or not. And the definition is that what I would need to do is I would need to show that literally every single contour integral from A to B. So I'll just draw some representative arrows of f. Every single path that you could possibly think of, all infinity of them from point A to point B, have the exact same value along their contour integral. So that would be the definition of a conservative force. I don't have the patience to do all infinity. So we're going to come up with a clever way of doing this. So here's path 1. And then here's path 2. And they both go from A to B, so I'll put an arrow on them because that'll be important later. So there. So by definition, f is conservative if integral along contour 1 f dot dl equals integral along contour 2 f dot dl for all contour 1 and contour 2. Super crazy. There's not a single one that we can think of for which that's not true. Gross. Anybody have seen the proof or sees the proof? There's a reason why we're doing it today, I guess. Does this look like something we just did?
Yeah, it looks sort of like Stokes' theorem.
Exactly.
Like, yeah.
So Stokes' theorem says this. Integral, and we'll use f, integral f dot dl equals integral surface dot d sigma, right? And it looks like we almost have this closed loop, right? Any two paths, provided I flip one, will turn into a closed loop, right? You dream up these two paths. I don't care what two paths they are. They both go from A to B. All I have to do is the following. So we'll flip one path and then we'll put it on the other side. Flip C2 and rearrange. And what I get is C1 integral f dot dl plus C2 flipped. So we went from B to A and not A to B equals 0. So we flip the limits of integration that gave us a minus sign, and then we put it on the other side so we get this, right? And now all I have to do is flip that arrow. And now voila, I have exactly this thing on the left-hand side. I have a closed contour, okay? So in a different way, and this is literally just the definition of a conservative force, is this is true for all loops, right? So if the closed line integral is 0 for every loop that you can dream up, then it's also a conservative force. Okay. What must be true if this vanishes for all loops? Well, if we look at Stokes' theorem, what does this say about Stokes' theorem? So, or integral S f dot ds, or d sigma, for all what's? So the old way of saying it by definition, this closed line integral vanishes for all loops. But if we invoke Stokes' theorem, then we can say that this is true for all, not loops, but the integral is now over surfaces, so for all surfaces. Even an infinitesimally small surface in like one particular place that I chose. So if an integral vanishes for every single possible arbitrary choice of limits, what must be true about the integrand, the thing inside of the integral?
It has to be 0.
Yes, because the surface itself is arbitrary. If there's even one spot where it's non-zero, I can just like move my integrand over there and take that integral over that teeny tiny non-zero piece and make this non-zero. So if the surface is arbitrary, this implies that the curl, the integrand, is 0 everywhere. Every single place. Okay, so we just proved the following thing. So we proved that f is conservative if curl of f vanishes. And the amazing thing about that, technically if and only if, the amazing thing about that is we went from having to integrate over an infinite number of unknown paths, so integral calculus is always harder than differential calculus, to just differentiating once. You know, granted, it's not like the easiest differential ever, but whatever. It's much better situation than we were in. Okay. So let's do the easiest example possible. Let's do gravity at the surface of Earth. So before doing that, any questions about what just happened? Okay, so, I mean, if anything, this is just like a mnemonic for this conservative vector field really is the thing that you guys are talking about in mechanics. Okay, so what is the force of gravity at the surface of Earth? That's f of x, y, z equals minus mg k hat, right? It points in the negative z direction, and it's mg big, where m is my mass, which somehow Earth knows what my mass is, which is a mystery that you guys will unravel in GR. Okay, if I want to show that this is conservative, then I do this, take its curl, d by dx, d by dy, d by dz, and then 0, 0, negative constant. And yeah, it's, you know, it's not even like really worth, so it's just like a constant, so all the non-zero ones show up. So this is 0, 0, 0. So the curl vanishes. So this is a conservative force. Okay, how that shows up in practice is, you know, maybe you could think about a parable of 3 triplets. And the 3 triplets start at the bottom of a cliff, and they all climb to the top. And they're going to jump into a sufficiently safely deep river below. And the triplets all have the same mass. So which one hits with the greatest speed? Of course, you're like, they're triplets, they have the same mass. Not like that even matters with gravity, but they're going to have the same speed. And then I try to beguile you by saying like, yeah, but this one took the most direct path up. This one took a path where they did more work, and then this one took a crazy path where they tried to do as much work as possible. Totally irrelevant, right? So they all have the same potential energy, same endpoints. Same potential energy. Same ability to increase their kinetic energy, right? So from a practical standpoint, that's what conservative forces mean. And mathematically, these are the following relationships in between those 3 ideas. So the following 3 things are different ways of expressing the exact same idea. Is that there's a potential energy function. That's true if and only if, by our definition, the force is conservative, and we have that weird kind of path integral condition. And then what we just showed is that, let's make this simpler to deal with. And we can show that that's if and only if we have a vanishing curl. And what we haven't done is this yet, but we will do that. So all of these things are totally equivalent, right? Curl of a vector field vanishes. Any path you take will, with the same endpoints, will give you the same value. And there is a scalar function, which in physics we call the potential energy function or potential function, which we can use to keep track of these endpoints. Okay, give you guys 1 second, and then we'll do 2 of those things as practice. If you guys need more practice, we'll take more practice. Okay, so now the game is I give you guys like goofball vector fields, and you tell me whether or not they're conservative and potentially find their functions, their potential functions. I'll write up both parts now, but we will go over the second part. So finding the potential function. And give you 2. You can probably guess how this is going to work out. And okay, any guesses before even touching pencil to paper? I mean, you can guess all you want, doesn't cost you anything.
I'm gonna guess B is gonna be non-conservative.
It's kind of swirly, right?
Yeah.
Yep. Cool. And check back in like 3 minutes. Should probably be enough for both of these. Okay, so everybody's suspicions proved correct. Is A a conservative force or non-conservative? Conservative vector field.
Got conservative.
And to really kind of start beating a dead horse here, did you integrate all uncountably infinite possible paths over all uncountably infinite pairs of endpoints, or did you take the curl?
Yes, very quickly.
Okay, so curl of A, Cartesian coordinates, because we're not non-Cartesian yet. We got I hat, J hat, K hat, and d by dx, d by dy, d by dz, and we have x, y, 0, and that I get nothing minus nothing, and then I get nothing minus nothing, and then I get nothing minus nothing. So that's the 0 vector everywhere, not just at one point, everywhere. So this is conservative. And then I'll do the same thing with curl of B. I hat, J hat, K hat. D by dx, d by dy, d by dz, minus y, x, 0. And then we have, okay, d by dy of 0 is nothing, d by dz of x is nothing, so that's 0. So for the j hat component, we get d by dx of 0 is 0, d by dz of y is 0, 0. And then for the k hat component, we have d by dx of x is 1, minus d by dy of minus y is minus 1, minus minus 1. So 1 minus minus 1. And then you could write this 0, 0, 2, or you could write this 2 k hat. So this does have curl, and we'll talk about what this means. So this actually has curl everywhere. This is, but we only needed 1 point, even 1 point at which this doesn't vanish. We would call this non-conservative vector field. Okay, so let me show you how this looks on those vector fields really quickly, and then we'll find the one potential function that we have. Okay, so you guys see the Mathematica? Cool. Just gonna vector plot this. This was the first function, so this is function A. So this is the conservative one. And then I'll draw 2 easy contours, but you know, it works for all of them. So let's say that we want to go from point A to point B. And then I'm going to do it in this way. And you can kind of see that like the forces are all perpendicular to my contour. And then I go back from B to A along my closed loop, they're all perpendicular. So the interesting thing is if I deform this or if I go straight through, so here, all the way there, all the way back, some are pushing against me, some are pushing with me. You can kind of see a little bit, I guess, how this could be conservative, but without calculating the curl itself, it's going to be really hard to prove. Okay, so our non-conservative force, all we would need is a counterexample, and that was minus y is the x component and x is the y component. So, aha! So really clearly I can see a counterexample with this. So now I'm again going from point A to point B. And then here, as I go from A to B, what would be true about integral b dot dl along this path 1? Positive, negative, or 0?
It'd be positive.
Yeah, so every single one of these b's is pointing in the same direction as my dl. So this is a sort of like maybe geometric logic that you guys have seen with magnetic fields. And yeah, this looks a lot like a magnetic field. So this is definitely positive. And then I want to go back. Again, all I need is a counterexample. I go back this way from B to A. So that's greater than 0. And then same exact logic, integral b dot dl. I have all of these vectors pointing in the same direction as my dl's. That's positive 2. How on earth am I ever going to add two positive numbers and get 0? And likewise, you can see that this is kind of curly. It's got that same sort of circulation. Right? So that's kind of the intuition for it. And gravity, springs, electric fields, you've never seen anything that looks like this. The weird one is the magnetic field, which does look curly. And we'll talk about that as a counterexample, definitely in this class. Okay, so second part of the question is we have a conservative force. This means that somewhere out there in the space of all possible functions, there's a potential function. And the potential function could satisfy the following really nice property. Essentially what's going on is like the thing is pre-integrated for you because the only thing that matters are the endpoints. That means that there exists some function of x, y, z that you just put in the endpoints, and whoops, and the difference so you at, I'll just say point A and you at point B is this path integral from A to B of f dot dl, right? You don't have to keep laboriously integrating the thing over and over and over. It's already pre-integrated. So that's what a potential function does for you. If the paths are irrelevant, you don't have to worry about the particular path. Okay. So the question is, what is it for this function A that we've decided is conservative? So the way you find it is there's a little bit of logic that goes into it, but it's really just write out what the gradient is. So negative gradient u for some unknown function of x, y, and z equals A, right? Conservative, curl free, therefore this is true. And so what that means is component by component minus partial u with respect to x minus partial u with respect to y minus partial u with respect to z equals A. So that's x, y, 0. And this means there are 3 individual, very easy differential equations. However, you got to remember one fact about the partial derivative. So the first component tells me this: partial u with respect to x equals x. Okay, what does that mean about u? So first just treat the partials like non-partial derivatives. If I just said like, look, I'm looking for a function whose negative derivative is x, what's that function?
Negative x squared over 2.
Exactly, right? So minus 1/2 x squared. Okay, and you would also say plus c. This is the new part about undoing partial derivatives. What if c was the following function, for example, natural log of z? The partial derivative with respect to x would just completely get rid of that, right? So in fact, any function of z only and any function of y only would be destroyed by the partial derivative. So when we're talking about partials, we don't have integration constants. We have integration functions of the non-partial derivative variables. So I'll just call it g of y and z. So there's this entire function, and it could be the most complicated thing possible, but as long as it depends on y and z only, that partial x would toast it. So this is u of y, x, y, and z. Okay. So the next thing we have is partial u with respect to y is equal to y. So what does that tell me about u? So first treat it like a non-partial derivative.
The same as in the x coordinate.
Yep. So I have minus 1/2 y squared. And then this is a different unknown function, but it's got to be a function of which two variables? In this case, x and z, right? Any function of x and z only would be destroyed by the partial derivative with respect to y. And then finally, we have the easiest one, 0. And this means that this is some constant. We could throw the constant in with the other variable. We could just say it's like, you know, I don't know what we're on. We'll just call it c. C of x and y is u of x, y, and z. Okay. So what we have is, just by comparing these, after you integrate all of them, you should be able to match, like, okay, I have this unknown function of z, but that unknown function of z there'd be information that I would get from the partial derivative with respect to z. And that information is that its derivative is 0 or it's just a constant. So essentially, the last step is I just match these. My function c of x and y needs to be the two things that I did have integrals for, the minus 1/2 x and y. So finally, by matching these, what I get is, I'll put it here, even though it's kind of gross board work, literally the last thing I write. U of x, y, and z is equal to minus 1/2 x squared plus y squared, grouping the terms, plus, we'll give it a good name for our integration constant, u of 0. Okay, what's the thing that I should do to make sure I got it right? So I should check this by taking the gradient of u. And if I took the gradient of u, what I would get is negative gradient of u. I would get x, y, 0 as the negative gradient of u, which is my force in the first place. So really the trick is just remember that they're partial derivatives, and what you would get if you took a partial derivative of any function of z, took its partial with respect to x, it would be gone. So you got to write these unknown functions down and compare. So check minus grad u equals x, y, 0, check. Okay, that's about all we're going to talk about these right now because, again, we're more interested in the mathy stuff. We're going to go into curved coordinates and try to do that before you guys see Fourier series and transforms in, I think it's like chapter 5 in Taylor. But any questions about that stuff? So at this point, that's everything that's on homework 2. So you should be able to do all of homework 2, and we can have like question time on that at the beginning of Tuesday's class. Okay. Like always, I can stick around for as long as people need after class today, but otherwise there will be some videos up before the weekend, and I will see you guys on Tuesday.
Awesome. Thank you.
Thank you.